The topic of this video is looking at how to write the equation of exponential functions. We're going to be looking at two examples. The first one from the test 3 review, number 6, is looking at how to write a possible equation for each of these data sets, and we need to determine if it is linear or exponential or neither. So these are 4 separate data sets. They all have the same x values, but I have y values for f, g, h, and k functions here. So if I look at the f data first, the y value 80, 40, 20, 10, and 5, I see that these values seem to be dropping by half. So half of 80 is 40, half of 40 is 20, half of 20 is 10, half of 10 is 5. So that is a multiplicative change. So I notice that the function f of x is going to be exponential. Because instead of an additive change, we're adding or subtracting a value, we have multiplicative change. And our b is, our base, our multiplicative change is 1/2, right? So we are multiplying by a half each time. Now, here I do have the 0 value for x, so I can say that my y-intercept, my a value is 80. So I can write my function f of x as 80 times 1/2 to the x. If I didn't know the a value, if, for example, my chart started, let's say, right, made a red box there. So if my chart started at 1 or something like that, if it started at 1 and 40, or even at 2 and 20, I could use the opposite of b, which is multiplying by 1/2, and I could multiply by 2 to go up the list. So if I started at 20, I could say, well, the value for 1 would be twice 20, which is 40. The value for 0 would be twice 40, which is 80. So I might not have the a value initially from a chart like this, but I can find it if I can find the pattern for b. Okay. So let's go ahead and look at the other functions, identify their types. The g of x function also starts at 80 and also goes down to 40, but then it goes down to 0. So I can see that the difference between 80 and 40 is a matter of 40 units. So half of 80 is 40, but we don't have half of 40 again right here. I go down by 40 again. So this seems to be a subtractive difference going down by 40, not by halves. So I can't identify the pattern based off of just 2 values, but if I look at all the values in the list, in f of x, I can see that they were halving. Here in g of x, I can see that they are decreasing by 40. So my g of x function is linear. I can see an additive decrease with a slope of -40. Once again, I know that the y-intercept value is 80 because of the 0, 80. If I didn't know that, I could add 40 to go up my list. If I started with, say, 140, I could add up to the 0 value of x by adding 40 and get the 80. But it is here in this list, so I can read it off that value. So our g of x function is -40x plus 80. We'll go ahead and look at the last two in this type, and then we'll also look at the next type of these later on in the test review. So the next function, h of x, if I look at my y values, 5, 15, 25, 35, I can see that that is going up by 10. 5 plus 10 is 15, 15 plus 10 is 25. If I add 10, I get 35, I get 45. So that means that h of x is linear, and that my slope is a positive 10 because we're adding 10 each time. The b value, the y-intercept value, is 5, 0, 5, top of the list there. So h of x is 10x plus 5. And we'll just go ahead and do the last one here as well. The k of x function, I still have 5 and 15, but after 15 I go to 45 and then to 135. So that seems to be increasing by a multiple of 3. 5 times 3 is 15. 15 times 3 is 45. 45 times 3 is 135, and so on. This is multiplicative change, so this is exponential, with the base of 3, that's our multiplicative increase, and the a value, which is the y-intercept for our exponential, of 5. So our function for k of x, a times b to the x, is going to be 5 times 3 to the x. Right, so those were exponential functions and linear functions when I had a bunch of data known to us, data where I could discover the pattern for the change, whether it was additive change or multiplicative change, to decide if it was linear or exponential. There's another type of example. I got to scroll down a little bit through my review to find it. I believe it was number 16. There we go. Number 16 says find the equation of exponential curve that passes through the given points. Now, there are two examples here, A and B. In these, I don't have enough points that I could determine a pattern. I just have 2 points. So I'm not going to be able to treat these the same way that I did the previous, where I was able to establish a pattern over multiple points. As we saw in these ones, it could be linear or exponential with just 2 points, but you have to have at least 3 or 4 to be able to see the pattern. Luckily here, we are told in number 16 that these ones are exponential. So I know for these, I must write an equation of the form y equals ab to the x. The problem becomes finding what a and b are. Okay, so in part A, we have the ordered pair 0, 5 and the ordered pair 4, 83. Now with 0, 5, because specifically I have that 0 as the x-coordinate, that tells me that the y-intercept, the a value is 5. So I already know part of my equation. So I know my equation is y equals 5 times b to the x. I don't know b yet, but I do have another ordered pair that I'm going to plug in for x and y. 83 is the y value, equals 5 times b to the 4th, that's our x value. And we're going to solve this for b. So we're going to divide that 5 from both sides. Let me get a calculator to work with here. Okay, so I'm going to divide 83 by 5. I know that's going to come out as a non-repeating decimal, so it's okay just to write that as 16.6 equals b to the 4th. And then the inverse of b to the 4th would be raising both sides to the 1/4 power, the reciprocal power. So we're going to do that next. Raise both sides to the 1/4 power, as those powers will multiply to 1 and give me the b by itself. So I'm going to take the 16.6 raised to the 1/4 power, and I get 2.0185 for b. Typically, we'll round that to 3 or 4 places. I went ahead and kept 4 places on that. So my equation for this one, number 16, is going to end up as y equals 5, that's my a value, times 2.0185 to the x. If you had only rounded it to 3 places, there was a 4 followed by a 9 here, so to 3 places it would have stayed as 5 times 2.018 to the x. It's not going to round to 9 because that place has been rounded to a 5. It was not originally a 5, but I went ahead and kept 4 places. I wasn't told how many. I don't think it was anyway, so 3 or 4 places is typical. Okay, now even though we're in the same question, part B is going to turn out a little bit differently, because if you take a look at those 2 points, I know that y is equal to ab to the x, but if I look at my 2 points, I have 3, 10, and I have 8, 2. The difference in part B is that I don't have 0 as the x-coordinate in either one of those points. So unlike part A, where I immediately knew the value of the y-intercept, the a value in the equation, I don't have that same information here. So we have to proceed differently on part B. All I know is that these values are x and y values for this equation. I don't know that values for a or b, either of the parameters, but I can still plug these values in for x and y in my equation. I typically like to take the point that has the larger x coordinate and evaluate that one first. So I'm going to plug in the 8, 2, 2 for the y value, equals a times b to the 8. And then we're going to do the same thing with our other point. The y value is 10 equals a times b to the 3rd. From there, in order to solve for a and b, if this was a linear situation, we could use substitution or elimination, where we would add the two equations. But in an exponential equation, since they're not additive, they're multiplicative, we're going to divide the two equations. The biggest benefit in dividing these two equations is that when I divide a b to the 8th by a b to the 3rd, a divided by a cancels. So I'm going to be able to get myself an equation that just has b's in it. So I'm going to take 2 divided by 10, that's 0.2, and a divided by a is 1, there's no a's left. And then I have b to the 8th divided by b to the 3rd. I'm going to use the subtraction of those exponents and get b to the power 5. Now I have something that I can solve for b. So we'll raise both sides to the reciprocal power again, the 1/5 power. And let's go ahead. I have my calculator still pulled up here. 0.2 to the 1/5 power gives me 0.7248 for b. Again, you can keep 3 or 4 places. Both are typical. I kept 4 to be consistent with what I did in the last one. All right. Now I know b, but I don't yet know a. So I'm going to plug the b value into one of those equations. I like to plug it into the equation that has the smaller exponent, because any error that I have accrued by rounding this value is going to be compounded fewer times if I have to raise that value to the 3rd than it would be if I raised that power to the 8th. So I'm going to use the one with the smaller power. So I have 10 equals a times 0.7248 to the 3rd power. That's just the number. So I'm going to divide it over. And so I don't get extra rounding error, I'm going to divide it just like it is from both sides. So I can type 10 divided by 0.7248 to the 3rd. So I get 26.2631 for a, if again I'm keeping 4 places. So put those two pieces together. I have my a value and my b value. This equation is y equals 26.2631 times 0.7248 to the x. And if you kept 3 places instead of 4, that's just fine. I kept 4 just because I did the last one. I was trying to be consistent with how many places I was keeping. So 2 different methods for how to find the exponential equation between 2 points, and which one I will use is going to depend on what kind of points I have, right? It's going to depend on whether I already know a point that gives me the a value and then just need to find b, or if I don't know either a or b, I will divide the 2 equations, find the b, and use that b value then to find a. All right, I hope that helps you understand how to write the equations of exponentials in various circumstances. If you have further questions, please let me know.